So what I'd like to start out with today is to go over the frequently made mistakes from the programming assignments that you submitted on Thursday, I believe. Everybody who submitted an assignment should have my comments by now. If you don't have comments from me, it's something you need to talk to me about right away because something went wrong. Well, whenever it was, you should have comments, OK? So everybody should have your comments back by now. I'm going to go through the frequently made mistakes, things that people had problems with, and I'll be happy to answer questions. So a couple observations at first. For those of you who put effort into it, great. There's some people who really aren't putting any effort into it, not great. Keep in mind, again, your participation scores are based in part upon doing a good job of putting a good first effort in. So just doing very little is not acceptable. So you get docked on participation as a result. So let's talk about some of the things. Some of the things were leftovers from the previous assignment. There are a bunch of people who didn't address my comments from assignment 1B, and so make sure you do that. The next thing that's due, which is due very shortly, is going to be the final submission, and you'll have to have everything done at that point. That's the one that's going to be graded. No more feedback at this point. It's for real. It's going to count as a grade. So here is an example. A bunch of people did this kind of thing left over from the previous assignment. The problem with this solution, as you can see up there, is that you go through the map one element at a time in the key set, but then the call to replace is made. And that's inefficient because that has to start and research everything from the beginning. So that's extra work. You don't need to do that. So don't write code like that. Here was another method that was implemented in a very strange way. I'm not quite sure what was going on, but a couple things. First, try to get in the habit of always using try-catch blocks to make sure that locks are always released even if an exception is thrown. Sometimes you'll have code that will not be throwing an exception, but it's just a good habit to get into, so make sure you use try-catch blocks and make sure you put the unlock in the finally part of that. There's a call to signal here. I'm not quite sure what that was doing, but that isn't necessary. Yeah?
As I'm not really too familiar with Java, the syntax too well, but like, do you only use a try catch if it says like public penalty required catches a certain exception, or can you?
No, I think what you're talking about there is exception specifiers on methods. But using exception specifiers on methods is completely independent of whether you use try-catch or try-finally blocks. In this particular case, you really want to use a try-finally block because you want to make sure that the lock is always released, even if an exception were to be thrown.
What's the difference between a try-finally and a try?
Well, so it's a try block. Try-catch would be catching an exception, and sometimes you need that. And there are examples here where we can use that for things like catching interrupted exceptions. But finally is something that always gets executed no matter what. So the finally block always gets run even if an exception is thrown. So that's something good. If you don't understand what the try finally is or try catch, I recommend you take a look at some of the online resources or go back and watch the videos that are online that talk about Java. I hope people could be able to catch up pretty fast on that stuff. So here's a bunch of problems. This is another thing I saw in looking back at some code from assignment 1B. So this is a better approach, right? We're going through and checking to see if each element that was in the entry set or the map set is in fact what we want. But the problem here is that there's nothing being set, right? So we're checking to see if the item is available, and then we're returning it, but we're not setting it to make it not available. So that means you're going to end up with really, really strange results. When I see code like this in submissions, it means people aren't running the tests because there's no way the test should work with code like that. So really get in the habit of running those tests. They're there for a reason. And if the tests are failing, make sure you figure out why they're failing rather than submit stuff that doesn't work. So that's clearly got a bug in it. Here is another issue. This one isn't really a bug. It's just that you don't need to allocate a new Boolean. You don't need to make new Boolean. That's extra work. You can just use false. That'll work fine. Here's another problem. This person's kind of got it right. They're checking each element to see if the element's value is true or false, but then they're calling replace. You don't need to do that. That, again, is going to have extra overhead because you're starting from scratch and searching through the list, through the map. Okay, so now we're into the simple semaphore implementation, which was the focus of assignment 1C. So a number of people, not everybody, actually most people got it right, but a number of people were doing stuff like this. They were saying private int number of permits. What is wrong with that? Why is that bad? What's it going to do? Well, first of all, what does volatile do? Remember, we've talked about volatile.
It shares caching and for the different threads. It makes sure that the threads access the values from the memory, not the cache.
Right, exactly. So Hamid is absolutely right. So what volatile means is don't use the cached value of this, which would be cached in, say, a core, processor core. Instead, make sure things go back to main memory. That's one thing it does. There's a second thing it does as well, in addition to making sure it uses memory instead of cache. What's the other thing that volatile does? Well, so it propagates, yes, but what's the key thing it's also doing that's really important here in the way it's being used? So what do you do with a volatile? What are the two operations you can do with a volatile? Exactly. You can read and write to it. So read and write, and what's the property that makes the volatile useful for reads and writes? What is it going to do? Atomicity, right. So they're atomic. So you get them all or nothing. Remember we talked about all or nothing? And I showed you the transporter thing from Star Trek or whatever, right? It's either going to be one value or another. It's not going to be half of something. So you need to make that be volatile, and you'll see why we need it when we get a little further down. Here's another example. This has a bunch of things wrong with it. First of all, get in the habit of using private so that it's not accessible to people outside. That's important. Secondly, don't use atomic integer because atomic integer is overkill for this assignment. It adds more than we really need here. And then thirdly, what's wrong with putting static here? What does static mean? Right, so all the instances of semaphore, simple semaphore, will share number permits. Well, what's going to happen then, right? Chaos and insanity. So if you have more than one of these things, they're going to be sharing the count. And of course, you want each semaphore to have its own, simple semaphore to have its own permit count. So this has a bunch of issues. Here is, so there's a couple of things here. First of all, you never ever need to, well, let me rephrase that. When you're accessing fields within when you access non-static fields within a constructor, you should never have to lock it. You never have to lock the access. Why is that? What's the property of a constructor that means you don't have to lock it for concurrent access? I'm sorry? It's only called once in one thread, right? A constructor is only called once in one thread. So it's not going to be called for multiple threads. Well, if multiple threads are calling your constructors, man, oh man, has something gone wrong, right? It's like Java doesn't work. So that's one thing. The second thing, and this is really more back up to the permit issue, and again, this is not happening, but imagine we were just in some other situation. If you're reading or writing to something that's properly marked as volatile, you don't have to put locks around it because those calls are atomic. That's the whole reason we use them. All right, now let's get into the myriad problems people had in acquire and release, but acquire was the big one that people had problems with. All right, so first of all, let's take a look at the thing up there. Assume for sake of argument that that's what that code looks like, and there's nothing else in there except my comments and the get and decrement. So first of all, we should be using volatile variables, so we don't need to call get and decrement. That's extra overkill that's unnecessary for here. So what's missing in this case? Exactly. So there's nothing in there that's checking to see what the current value of permits is. What's the key property that you have to ensure is true before you can actually decrement the account? It has to be greater than 0, right? So that's that check, which, by the way, needs to be done in a loop, as we'll see that people got that wrong later, too. That's what's called a guarded expression. So what that says is you can't get further than this loop until that condition is true. That's what the guarded expression means. Very important. OK. So the second acquire, the one where it says yikes, what's going wrong there? Well, let's assume for sake of argument that that's handled somewhere in there, but that's what the ... will be. What's
the synchronize this kind of overkill in this situation?
No.
Shouldn't synchronize come before checking the available permits?
Yes, and why is that?
Because it should change between those two steps.
Right.
Some other difference.
So the key point is, in a concurrent program, never access shared state. In this case, shared state would be available permits. How is it shared? It's shared between different threads that are trying to acquire and release it, or acquire it. So we're checking the value of permits outside of the lock being held, which completely defeats the whole point of having synchronization, right? You want to make sure those things are protected. So that's problem number one. There's a second problem here as well, ignoring for a second that this is also not being protected properly. There's another problem here too. What's the other problem? Something else that's missing. Exactly. Very good. So the check isn't in a loop. Why do we need to put that check in a loop? What's the reason for putting it in a loop? Because if it's not yet greater than 0, we're going to wait. But then when we wake up later, it may still not be greater than 0, because these things can be happening concurrently. So another thread could come along and grab it before we have a chance to loop back around again.
So inside that loop, what do we put in there? Just wait, or do we give it a certain amount?
Right. So it kind of depends which of the acquire methods are going to be used. So if it's acquire that's the one that can be interrupted, then it's going to work slightly differently than if it's the one that is not acquired, if it's acquired uninterruptedly. But in general, you're going to wait, and you're going to typically, well, they both end up working more or less the same way. You're going to call wait, and then when wait returns, you're going to loop back around again and check to see if the condition is true. Now, keep in mind the way that wait works is that, well, and this is why you always want to make sure that these things are called with the lock held. So you have to put them in synchronized statements. So we'll assume for sake of argument that we flipped it around and synchronized is outside of the call that's checking the permits. So with the lock held, whenever you call wait with the lock held, and you should always make sure it's called with the lock held. This is true both for the version that used reentrant lock that the grad students did, or the version that's the monitor object version that the undergrads did. The lock always needs to be held when you check the condition. Otherwise, you'll have race conditions on that state. When wait is called, it will atomically release the lock, either the mutex the mutex lock for the monitor object, monitor mutex or monitor lock, or the reentrant lock. It'll automatically release that and go to sleep. It's atomic, so that's not your problem. That's what the JVM or Java's libraries have to do. When wait wakes up again, but how does wait wake up? What causes it to wake up? Something's going to notify it or signal. We'll talk more about the difference later. So when something is notified, then wait will awake, but before wait returns, it first reacquires that lock. So if you put it in a loop, whenever you're checking the condition inside that loop, while condition or expression, the lock's always held. Really important to remember that the lock is always held when the condition's checked. And so when wait returns, it actually has to reacquire the lock. So going back to Duncan's question. So Duncan's question was, what goes in there? Well, you've got to wait, and then when you return, you'll loop back around again. Now, there's some other things you need to do if it's the uninterruptedly version. We'll talk about that in a second. Okay, any other questions about this? A lot of people had issues. Yes, Yifan. Yeah, ignore the timeout. The timeout was going to be something I was going to put in there, and then I realized something interesting. You can do a timeout very easily for the grad student version with condition objects and reentrant locks, but for some reason that escapes me to some extent, Java's monitor object wait call that's timed out is somewhat broken because it doesn't really tell you that a timeout has occurred. It just returns. And so it's very hard to know why it returned. Did it return because you were notified? Did it return because it timed out? And if you take a careful look at the await call, the timed await call in the condition object, it returns true or false to indicate whether it timed out or not. Whereas the wait method doesn't. It's sort of a botch. So I kind of withdrew that particular version of the assignment and updated the skeleton. So make sure you pull the new version. You should have a comment in your code saying pull the new version that doesn't have the timeouts. So don't worry about timeouts for now. All right, now let's take a look at acquire uninterruptedly. Now, acquire uninterruptedly is much more interesting because that's the one we're actually using for the assignment. And this is where things get interesting. So first of all, await uninterruptedly does in fact do the trick. So the way that await uninterruptedly works, if you call that, this is for the grad student version, is that await uninterruptedly will ignore interrupts, but when it returns, it'll set the interrupt status flag properly if an interrupt had occurred. The one thing you have to be careful of is that you don't make subsequent calls that will reset that flag. So make sure you're careful about that. And there's other ways to implement this. My particular version doesn't, my particular implementation of the grad student version doesn't use await uninterruptedly. What I do is I put it in a loop. I call await. And then if await returns and a timeout occurred, I mark that with like a Boolean flag so that when I'm finally done with everything, I can check that flag and set the interrupted status manually as needed. A bunch of people had this code. What's wrong with this code? Let's assume for sake of argument that the while loop is correct. But what happens? Why is catching the interrupted exception and then setting the interrupt flag, why does that not fulfill the specification?
Isn't it already interrupted if they have an exception?
So it's been interrupted, and we're about...
If it throws while it's in the loop, it won't continue to throw.
Exactly. So the key point here is that acquire uninterruptedly is not supposed to return if an interrupt occurs. This implementation will note that an interrupt occurred, and then it'll return, which is violating the spec. The spec was it's supposed to be await or acquire uninterruptedly, which means you don't want to be interrupted by an interrupt. So that's not right. Here's another problem. A lot of people did this one. So let's assume for sake of argument that this is correct, and they're catching the interrupted exception, which is good. But then what they're doing is they're setting the interrupted flag and then looping back around again, which means that this thing might get swallowed by some other call in here. So rather than calling this thing, you need to set a flag that you can then check at the end of the method after you've dropped out of all this stuff, and then set that call. We'll talk in more detail about the interrupted flags later, probably on Wednesday. OK, and then there were a bunch of common problems in release. So what's the most obvious thing you can see that's wrong here? Should jump out at you what the problem is. Right. So we're incrementing a field, m permits, outside of the synchronized statement, which means that, again, race conditions will occur, which is bad. What's another problem that's there?
To get the edge case,
What?
to make sure that it's not null. Like
It's notifying everyone.
Right. So it's notifying everything. And we don't need to notify everything. We just need to notify one. There are situations, by the way, where notify all is useful. This is not one of them, but there are uses for it. But this is overkill, because we're waking all kinds of things up, but only one's going to be able to run. So it's better just to use notify. All right, that's the second problem. What's the third problem? The third problem is more subtle. It's not really a problem. It's an optimization.
Notify should be outside.
Outside what?
Outside the synchronized.
No. You don't want to call notify outside the synchronized. That'll cause all kinds of problems. I think you'll get an illegal monitor exception or something like that. Yeah.
You only need to notify one.
Right. So we should change notify all with notify. That's correct. But there's another thing as well that it's a subtle thing. So the problem here is, or not the problem, the optimization is not applied. What if the count is, if the semaphore count is still less than 0, should we be notifying anybody? No, because nobody's going to be able to do anything, right? So you should only call notify if the permit count has now gotten greater than 0 or equals 1 or whatever. Probably checking greater than 0 is a little bit safer. So you can optimize this by only calling notify if there's somebody who could possibly wake up and make progress. Otherwise, there's no point. Yeah?
So why would our permit count drop below 0?
Because you might start out with a bunch of threads. Let's say you started out with a binary semaphore, so it's 0 or 1. So one thing can go in. And then you had a bunch of threads come along. And they all call acquire. So it'll either drop, it depends how your implementation works, it'll either drop below 0. Remember how when I talked about what a semaphore was, I said if the count is negative, it's a count of the number of waiting threads that are trying to acquire the resource. So think in your mind about the beach volleyball use case we talked about, where there's 2 courts and therefore 2 balls, but 18 teams have shown up who want to play. So you've got a lot of people who are sitting around soaking up the sun, not playing volleyball, waiting for the token to get greater than 0 so they can go play the game. That would be an example. Marianne, did you have a question?
I don't know if I'll ask it. For the range of block and the condition object, do you think it would ever go below 0? We need that check for that solution.
So there's different ways to implement it. Sometimes you actually have the count go below 0. Sometimes you just wait while it's 0. But the key thing is that there could be multiple things waiting if it's below 0. And you still have to do the check. Or it still is an optimization to do the check. There's a couple of different ways to implement that. OK, so any more questions? Now, I think what's worth noting about all this stuff is this is really not a lot of code, right? In other words, there was basically assignment 3 was a handful of methods. But it's very subtle code, and that's almost always the case with concurrency. So the key thing is to really sit down and think about why it works the way it does. Take a look at my comments. Take a look at the video with this stuff. Reason about it. Because in most cases, it's not this simple. And the point is, if it's tricky for something that's really simple, imagine what it's like when it's not really simple. So get in the habit of really understanding these things.